Hello, my name is Zhen. In this video, I'm going to show you two query optimization techniques we have implemented in Firebolt. Let's dive in. The optimization techniques we're going to talk about are related to correlated aggregate subqueries. Before going into the details, let's have an overview of the Firebolt query optimizer. In Firebolt, we have built a query optimizer from scratch. Today, we have PostgreSQL compliant behavior. When we say compliant, we mean not only syntax, but also semantics, like how we resolve functions, how we derive data types, and so on. We have about 150 optimization rules, including full decorrelation support. Our optimizer runs on and produces stack-shaped plans, and it also includes history-based optimizations, meaning the query optimizer can learn from queries executed in the past to make better decisions. Now, why we are interested in correlated aggregate subqueries? In Firebolt, we have observed that modern data apps often use SQL query generators. They could be tools developed in-house or well-known data tools that generate SQL queries, like Looker, Tableau, dbt, and so on. These machine-generated queries may contain very repetitive patterns with lots of redundancy. Query optimizers in database systems then need to detect and remove such redundancy so that queries still run fast. Let's take an example. This is a query derived from Firebolt production workload, but of course we have rewrite it using the TPCH schema. The query is straightforward. It selects on customer table, and then it utilizes a correlated subquery to select for each customer key orders matching status equal to O, and among all of those orders, select the order with the minimum total price. Let's just call this subquery to compute the minimum order. Now, at some point, the developer of the application decides, I need not only minimum order, but also need to compute the maximum order. Now, if the developer is about manually rewrite this query, probably we just add another max aggregate function into the subquery. But since we're using a query generator, the query generator will happily piles up another subquery for us. Why is that? If you think about it, the query generator is also a piece of software, and its development also follows general software development principles. If we have a function or a module that can produce such query pattern, and we simply will just reuse it, right? Okay, now sending this query to most of the database systems will yield a query plan that looks like the right side. The database system will try to decorrelate these subqueries one by one. So on the left side, it will scan the customer table, and by decorrelating the first subquery, we get a left outer join, and then the subquery is listed in the middle part. Here we scan on the orders, apply the filter, and then do the aggregation. Here the node 6 will compute the minimum order. Now, we will decorrelate the second subquery, and it will again produce another left outer join and then another aggregate node computing the maximum order. In this case, because the two subqueries share a common part, the two aggregate function will be computed on top of the same input. As I mentioned before, in Firebolt, we work on stack-shaped plans. So in this case, they actually share the same input data. In many systems, we produce tree-styled plans, and the situation can be even worse because the scan on orders may be duplicated, and we need to scan the table twice. This example motivated us about implementing the following optimization. We call it common aggregate discovery. In the example, we have multiple aggregate functions computed on the same input, but for some reason, they're spread in different places in the plan. But they could just be computed on the same input in a single pass. Now, if we abstract that pattern here, we see we have a join, joining the minimum order on the input, but then we also do join computing the max on the same input. If we can discover the aggregates on the common input, we will simply generate the plan on the right side. Basically, we remove one aggregate node, and we will simply compute both min and max in the single pass. Now, the same data will be used to join with the customer table twice. And with that, we're thinking, this still seems redundant, right? Can we just remove one of the join? After all, we are just joining the same thing twice. And here comes redundant join removal. Redundant join removal is not something new. This optimization technique has been discussed a few decades ago, and it is widely available in modern database systems. When we talk about redundant join removal, there are usually two cases. The first case is that we can utilize primary key and foreign key constraints to identify redundant joins. And the second case is when we know that a join will definitely produce empty result, and then we can know, of course, the join is redundant, and we can replace it with an empty scan. Here, we focus on the first case. In modern data warehouses, enforcing constraints like primary key or foreign key is very, very expensive. This is due to two reasons. Firstly, we usually have highly concurrent data ingestion nowadays. And in this scenario, enforcing a constraint like primary key check will hurt the data ingestion performance a lot. Secondly, it's just due to the sheer amount of data. As a result, many systems nowadays does not actually enforce constraints. But some systems might still provide keywords like primary key or foreign key and use them as kind of a query optimizer hint. So if the user knows this column is indeed the primary key, let the optimizer know, and the optimizer could utilize that. And to us, the question is, okay, since we don't generally enforce such constraints, can we still detect redundant joins without primary key or foreign key constraints? And the answer is yes. We extend the condition to recognize a join is redundant if the join does not duplicate or remove any input tuples, and also all columns required by the operators above the join can be provided by the join inputs already. And in this case, apparently the join is redundant. If we look back to our example again, we see we have a left join joining on group by A using a join key which is A equal to A. And then we have another left join joining on the same input using the same join key. And apparently, once we have done the first join, the second join becomes redundant because it's not going to change the result. It's not going to change the column. So in this case, we recognize one of the left join here is redundant, and we can simply remove and leave only one left outer join in the end. Now, with both optimizations in action, we finally get the final plan shown on the right side. And here we have only one left outer join, joining customer table on a single subquery, computing both min and max order, and we scan orders table also only once. And the equivalent rewritten query for this plan is shown on the left side. All right, now let's evaluate these optimizations in Firebolt. We used a TPC-H scale factor 100 data, and we started Firebolt one large compute optimized engine. And with the optimizations disabled, running the original query, we got around 2.69 seconds. And if we manually run the rewritten query, we get 1.4 seconds. Now, with the optimizations enabled, we don't really have to run the rewritten query manually. We can run the original query and we get 1.42, which is very, very close performance compared to the rewritten query. All right, now you have seen both common aggregate discovery and redundant join removal in action. You might have thought, oh, the example for redundant join removal is actually simple, right? After all, it's left joining the same input twice on the same join key. With a bit analysis, it's probably easy to detect that one of the left join is redundant. That's fair. And here, I'm going to show you a second example about redundant join removal. The query is again derived from Firebolt production workload, but is rewritten using the TPCH schema. Here we firstly define a max-ORed CTE. And if you look at the query in this CTE, it's pretty much the same as the subquery that we see in the previous example. Again, for each customer key, we're computing the maximum order. Now, in the main query, we scan customer table and then join with this CTE twice, using the same join condition. The difference is that when we join the CTE for the first time, there's a filter, filtering price smaller than 10. And when we join the CTE for the second time, the filter becomes a bit different. Now it's price smaller than 10, but also bigger than 5. This is also a very common redundancy generated by query generators. And in this case, we're still able to detect that the second left join is redundant. And why is that? Because the join result of the second left join can be fully derived from the join result of the first left join, because the filter here selects a subset of the rows. So with some careful rewriting, we could simply only do the first join, and if the query ever use columns produced on the null padding set of the second left join, we can simply add a case 1 expression saying if that column is bigger than 5, then we can reuse the join result of the first join. Otherwise, we know due to the left join semantics is null. All right. If you are interested in more details about these two optimizations, we have published a paper in BTW 2025, and the full article can be accessed through the QR code on the right side. And if you're interested in Firebolt in general, follow us for more content like this. On that, I hope you enjoyed the video. Thank you for spending time with me, and see you next time.